Today I'm going to present you a new lecture about chapter 3. In chapter 3, in the prior lectures, we've learned the general properties of the acids and the bases. And after that, according to the three different theories, we identified which compound become acid and which one become the base. And after that, we learned how to write the ionization reaction for the acids in their aqueous solutions. Well, actually, we have a plan to do some classification of the acids, but before doing that, we have to explain the problem. What's the benefit of that lecture? By the end of that lecture, you will know what is the conjugate, what is the conjugate acid-base pair, and the acid rain, the amphoteric compounds. So we have many things to be learned. Well, when we're going to prepare or when we want some aqueous solution of the acids, for example, I like to prepare the aqueous solution for HCl or H2SO4. Well, it's simply just mixing it with water and that's all. But what will happen inside of that solution under a macroscopic level? Well, we have a problem with the ionization steps. With what? Ionization steps. So actually there are many things we should know about the ionization process of the acids, mainly with the polyprotic acid. So we will start by the classification of the acids based on the number of the proton that can be donated. Based on the number of proton donation or donating the proton. Well, we have two types of the acids which are monoprotic acid. Okay, monoprotic acids. Well, from the monoprotic acid we will understand something. Monoprotic, it means single proton. Okay, the acid that can donate a single proton per a molecule of the acid. It means if we have one molecule of acid, it can donate only one proton. How many protons? Oh, one proton. So the acid that can donate one proton only per a molecule called monoprotic acid. When we say proton, it means hydrogen ion or hydrogen atom after releasing the electron, because of the nucleus of the hydrogen contains only a single proton without any neutron. So what will happen if you release that electron? It becomes a proton. Hydrogen ion is a proton. That's why we call the hydrogen ion as a proton, because of there's only one proton without neutron, without any electron. Okay. The example of the monoprotic acids such as HCl, CH3, COOH. Oh, teacher. Okay, it's very simple. HCl has one hydrogen atom. We know that it's monoprotic acid. But what about CH3COOH? It has four hydrogens. Look, 3 in here and 1 in here. But look, dear students, any acid that contains this group, carboxylic acid group, it will be classified as a monoprotic acid. So what about that 3 hydrogens? They are bonded to that carbon with a strong covalent bond. They cannot be released. That's why the only ionizable hydrogen is that one. So we will classify acetic acid as a monoprotic acid. Or HNO3. HNO3 can release only a single proton. So all the acids with that group are weak and monoprotic. They are organic acids. Organic acid. Acetic acid contains 4 hydrogen atoms, but it's a monoprotic acid. Why? Did you remember what I told you? The last hydrogen is ionizable, but the first 3 hydrogens are bonded to the carbon atom by strong covalent bonds. because it can only donate one proton. Which one? Look, I prefer to clean it. Which hydrogen atom is the ionizable? That one. But the three hydrogens which bonded to carbon atom, they cannot be ionized. Well, only one proton that is attached with the oxygen atom. Look, it's attached to the oxygen atom. Thus, it's monoprotic acid. Through this equation, CH3COOH plus H2O, because of its aqueous solution for acetic acid, to producing, look, it's acid according to Bronsted-Lowry. So from now on, we're going to depend only on the definition of Bronsted-Lowry. Okay, it's very useful. Our concern is Bronsted-Lowry. So it will release a proton to the molecule of H2O to producing hydronium ion, and after that it becomes an anion, okay, which is acetate. So it's monoprotic acid. Then the second type of the acid is polyprotic acid. Well, I prefer to do another example for the monoprotic acid. For example, HNO3 plus H2O. It can donate a proton to the molecule of water, but we should write a single arrow because of its weak electrolyte. It will be NO3 negative plus H3O positive, which is hydronium ion. They are aqueous, it's a liquid, and it's liquid. Okay. Superb. Now we know how we can write the ionization reaction for the monoprotic acids. And next, we have a polyprotic acid. The polyprotic acids, well, polyprotic acid, poly, it means more than one. The word of poly, the prefix of poly, it means more than one. Acids that can donate more than one proton. Okay, it's maybe 2 or 3. So for that purpose, we have diprotic acid. In here, it yields 2 protons, and in here it yields 3 protons. Triprotic acid, such as, well, for the polyprotic acid, we have diprotic and triprotic. Triprotic acid, such as H3PO4. It's very simple phosphoric acid, we know that. But about the diprotic acid, it can donate 2 protons per molecule of the acid, such as H2SO4, H2CO3. Well, it doesn't matter that the acid is weak or strong. And a triprotic acid, such as H3PO4, which is phosphoric acid. Well, actually, the problem locates in here. So we have a problem with the ionization reaction for the polyprotic acids. Well, teacher, it can donate 2 protons, diprotic, but how? Only by one step, or it's stepwise. Stepwise, it means step by step. Actually, for the diprotic and for the triprotic acids, we have the stepwise ionization reaction. It means the ionization reaction includes same steps by the number of the proton. It means 2 protons, there will be 2 steps of the ionization reaction. 3 protons will be 3 steps of the ionization reaction. Good. Well done. Let's see how we can write the ionization reaction for the polyprotic acids. If you understand here, so you will be a hero for the next slides. Good. Triprotic acids, I told you, it can donate 3 protons per molecule of the acid. So, aqueous solution of sulfuric acid is H2SO4. Oh, H2SO4, it has more than a single proton. It's diprotic, it's polyprotic. So the ionization reaction includes two steps. Why? Because we have two protons, two hydrogen atoms. Okay, the first step. H2SO4, we know it's strong acid. So it's highly ionizable compound. Highly ionizable compound yields product with the most concentration. That means we have the maximum concentration in here. The maximum concentration in here. Okay? But in here, because of its strong electrolyte, so it has a weak attraction force between the hydrogen, which is scattered, and the negative power, which is SO4. So it will break up into its ions completely by 100%. So assume that the remaining concentration of H2SO4 is 0. So it will convert to its ions by 100%. In here we have the maximum concentration, but in here we have high ionization. So the product of high ionization always, the product of high ionization step always has the maximum concentration. The product of the highly ionization step always yields or always has the maximum concentration. So we just release the first hydrogen to producing HSO4 negative. Okay, as much as we're releasing the hydrogen ion, so we should increase the negative charge from the above of the right side. From the top of the right side, we should write -1 after releasing the first hydrogen, -2 for the second hydrogen, -3 for the third hydrogen. Okay, now, is that finished or no? There's still one more hydrogen atom. So we should write the ionization step for that one also. HSO4 plus H2O. Look, the second step always has lower ionization power. And here we have less ionization. Why? Because of its negatively charged 1. So releasing that hydrogen under the force of that negative is too difficult. But in here it's neutral, so releasing the first hydrogen is easy. But the second step, it's charged, it's anion, so releasing plus from that anion, it's too difficult. That's why it's less ionization. The product of the less ionization, okay, contains less concentration. But for high ionization, high concentration. High ionization, high concentration. Less ionization, less concentration. So you see that now in the aqueous solution of H2SO4, we have how many particles? Well, H2SO4, no. It will be destroyed by 100%. H2O is not our concern. It's not our goal because of its solvent. So we get H3O in both steps. H3O in both steps. We have H3O in both steps. And after that, we have HSO4. Okay, you see, HSO4. And then we have SO4 -2, SO4 -2. Now, let's arrange them according to decreasing or increasing the concentration. We get H3O in both steps, so it has the maximum concentration. And after that, the first reactant, the reactant of the second step, then the reactant of the third step, then the reactant of the fourth step. Well, if we have 4, we don't have 4. So then, HSO4 contains more concentration than SO4. So, just like that, we can write the ionization reaction for the polyprotic acids. Therefore, in aqueous solution of H2SO4, we get the following ions. Ions. SO4, HSO4, H3O. Which one has the maximum concentration? H3O, and after that HSO4, and after that SO4. So, another one is really important. Aqueous solution of phosphoric acid. aqueous solution of phosphoric acid. Oh, phosphoric acid is triprotic acid. Well, teacher, I remember that you told me the first step always has high ionization, but why it has low ionization? Okay, it's weak electrolyte, it's weak acid. So for the weak acid, immediately we have high ionization, low ionization power. It's weak acid by itself. We cannot do anything. But the first example it was H2SO4, it's strong acid, high ionization. But this is weak acid, so it has low ionization. Well, suppose that we get the quantity of the phosphoric acid by that size. If it's weak acid, so only a small amount of that acid can ionize. Well, this amount only. The remaining will be H3PO4. So immediately, the maximum concentration remains for H3PO4. Now only that small amount ionizes to producing the ions. Black color, okay. Well, to producing H3O and H2PO4 negative 1. Why negative 1? Because of we released one hydrogen. And then we still 2 hydrogen remain, so we should get 2 more steps. Well, another step, H2PO4 negative 1 plus H2O to producing HPO4 negative 2. Why negative 2? We just release it, the second hydrogen. And then HPO4 negative 2 charged anion plus H2O to producing phosphate anion. Why negative 3? We release 3 protons, 3 hydrogens. Now let's arranging them according to the consequence of increasing or decreasing the concentration. Well, the maximum concentration is the electrolyte by itself, which is phosphoric acid, H3PO4. It's weak electrolyte. And then we get hydronium ion in all steps. So then hydronium ion, H3O. Then the reactant of the next step, then reactant of the next step, and then the last one. Well, teacher, actually, we almost confused it. Can you tell us the fast way and the most easy way to understanding or to writing the type of species that can be present in the electrolyte, I mean aqueous solution of the electrolyte? Well, I can tell you that. It's easy. Look, we have H3PO4. Now, release the first hydrogen. Well, immediately after the acid, write H3O. Whatever. H3O. I will write in here. Here we have enough space to writing that long thing. We get H3PO4. So H3PO4, when we put into water, it will produce H3O, and then release the first proton. The first proton. Okay, it will be H2PO4 negative 2. Oh, negative 2. H2PO4 negative 2. Release another proton, HPO4. Sorry, it's negative 1, not negative 2. It's negative 2. Okay? Because we just released the first proton, it will be negative 1. Second proton will be negative 2. Third proton to producing PO4 negative 3. Okay. It's weak or strong? It's weak. So it will have the maximum concentration. Then. Just like that. It's very simple. Another example, H2SO4. For H2SO4, when we put H2SO4 into water, so it yields H3O immediately and then release protons step by step. H2SO4 becomes HSO4 negative 1. Then another proton will be SO4 negative 2. Okay. It's weak electrolyte or strong, it's strong electrolyte. So it's gonna be disappear. It will destroy by 100%. So the maximum concentration is hydronium ion and then. It's least concentration, maximum concentration. Well, we have some kind of question which they are so similar together. Look, in the aqueous solution of H3PO4, we get how many particles? How many particles? So it doesn't matter that it's ion or it's neutral. Well, we have H3PO4, H3O, H2PO4 negative 1, HPO4 negative 2, PO4 negative 3. So, which species has the maximum concentration? H3PO4. Okay. Now, in the aqueous solution of H3PO4, we get how many ions? Oh, it's about ions. So, we should delete that one. Delete that one. Because of the question says, how many ions? We have that one, that one, that one, that one. They are ion. Which or what type of the ion in the aqueous solution of H3PO4 has the maximum concentration? H3O. What about least concentration? PO4 negative 3. I think now you get the point. Hopefully, of course. Well, let's go through these questions. So in the aqueous solution of phosphoric acid, Blanca present, we know that. Aqueous solution of HF, HF is weak electrolyte, so we get HF as the maximum concentration, then hydronium and next fluoride. For the base also we have some examples of the base. Well, take that example serious, please. Aqueous solution of NH3 produces NH3H2O plus, okay? So we get NH4 plus OH. Its weak electrolyte remains as the maximum concentration, then NH4 and after that OH. They have equal concentration because of it includes only a single step. Okay, that's enough about the ionization steps for the strong, polyprotic acids, even for the monoprotic acid. And now, when we put the acid and the base into water, they yield a compound, a new acid and a new base are formed. When we put the acid in the water, or when we put the base in the water, a new acid and the new base are formed. They have a potential to receiving a proton or to releasing a proton. Well, we will learn this phenomena in terms of conjugates. What are the conjugates? Conjugate acid and conjugate base. A conjugate acid, remember, we need a Brunel-Lowry theory, a conjugate acid and conjugate base. The species that is formed when a Brunel-Lowry base gains a proton. Oh, conjugate acid, it means when we have a base compound and when they receive a proton, they're gonna be Brunel-Lowry, they're gonna be conjugate acid. So how we can get conjugate acid? Oh, teacher, if we have a base compound and after gaining a proton, they'll be a conjugate acid. What about conjugate base? Of course, if we have the acid compound and after releasing the proton, it will be a conjugate base. Let's see. Well, actually, I don't understand what means by Brunel-Lowry base gaining a proton or Brunel-Lowry acid releasing a proton for the conjugates. Well, we have this example. Let's take a look about this example. When we mix HF, let's see, we have HF plus H2O. HF, we know that it's acid and it's base. Which of them can release a proton? Of course, HF to producing fluoride and ion. And then water becomes H3O as a hydronium ion. Now, it's acid, so it will remain amount will be conjugate base. Look, a conjugate base, when abronisted lowry acid has given up a proton. Look, we have abronisted lowry acid and it gives up its proton, so it will be a conjugate base. For the base, look, when abronisted lowry base gains a proton, it will be what? Conjugate acid. So H3O is a conjugate acid. Okay, you see that? Acid after releasing a proton will be a conjugate base. Base after gaining a proton will be a conjugate acid. It's very easy for understanding. Now we have some important questions. Take these examples serious. Look, how we can answer some questions where about a conjugate acid and a conjugate base. Okay. What is the conjugate acid for HS? Oh, for HS. Let's apply the definition for the conjugate acid. So, conjugate acid can produce when we have abronisted lowry base after gaining a proton. So, for creating a conjugate acid, look, this question says that create a conjugate acid from this compound, from HS. How we can create a conjugate acid, if you remember? Of course, we should have abronisted lowry base. And it should gain a proton, then it will be a conjugate acid. So this is abronisted lowry base, it's base. So it should gain a proton to be a conjugate acid. Oh, HS, -1. So put a proton into its formula, it will be H2S. Oh, H2S is a conjugate acid, for HS -1. Okay. What is the conjugate acid for HPO4 -2? Well, again, let's apply the definition of conjugates. Conjugate acid can produce when we have abronisted lowry base. So this is abronisted lowry base. It can receive a proton to be a conjugate acid. Oh, HPO4 -2 will be H2PO4 -1. Now it's conjugate acid. It's conjugate acid. You see this? It's conjugate acid. So the conjugate acid always has one proton more than the base. Conjugate acid always has one proton more than the base. Look, it's conjugate acid. It has one proton more than the base. It's conjugate acid. It has one proton more than the base. Ah, teacher, now I understand. When we want to create a conjugate acid, we should increase a proton. And when we want to create a conjugate base, we should release a proton. We should decrease the number of protons. Oh, that's very easy. Now I understand. If we want to create a conjugate acid, increase the number of protons. Creating a conjugate base, decrease a number of protons. That's all. We have this compound, HS. SS, HS. Let's create a conjugate base. A conjugate base, we should decrease the number of protons. Okay, decrease the number of protons will be S -2. It's conjugate base for that acid. So the acid always has one proton more than the base. In terms of conjugate, of course. What's the conjugate acid for HSO4? Oh, conjugate acid, we should increase the number of protons to creating conjugate acid. So it will be H2SO4 immediately. What's the conjugate base for HS? Oh, in that case, we should decrease the number of protons because it asks to creating a conjugate base. So we should release the number of protons by 1 because of it will be a abronisted lowry base. Actually, now we have more idea about a conjugates, but still we need more practice we have some noble questions. In this reaction, a chloric acid plus NH3 to producing ammonium and chlorate. Okay, a conjugate acid of NH3 is, NH3. We should create a conjugate acid for NH3, so we should increase the number of protons. Simply, creating a conjugate acid, increase the number of protons. For conjugate base, decrease the number of protons. So, do we get NH4 in this reaction? Yes, teacher. So the right answer is C. Well, a new thing. Conjugate acid-base pair. Well, it's very good subject. Actually, it makes its before and its after easier. It makes its before and its after things easier. How? Let's do it. A conjugate acid-base pair, the reaction that involves two acid base. Okay? When we mix acid base together, so they will be they're gonna produce their conjugates. So in that case, we're gonna have two pairs. Well, for example, we have HF hook. HF mixing with H2O. HF mixing with H2O. Well, it will produce, look, it's acid, so it will release a proton. It can donate a proton to the water to producing H3O, and then it will remain as an F anion. It's acid, so F is a conjugate base. Its base, H3O, is a conjugate acid. So what are the conjugate acid-base pair? Actually, pairs are differ from each other. Look, pairs are differ from each others by only a single proton, no more. We should have the same negative side, but for the positive side, we have the difference between them only by what? By one proton. For example, HF and F. HF and F, they are different from each other only by this proton. So it's conjugate acid-base pair. Again, we have H2O and H3O. They are different from each other by one hydrogen. So it's a conjugate acid-base pair. We have two conjugate acid-base pairs in this reaction. Okay? Do you remember how we can recognize the acids from the pairs? The acids always has one hydrogen atom more than the base. Look, it has one hydrogen atom, so it's acid. It has one hydrogen atom more, it's acid. You see, it's very easy. Now, how we can recognize acid and base from the pairs? For example, we have this pair. We have HSO4, -1, and we have SO4, -2. They are pair or not? Look, SO4, SO4. One hydrogen, no hydrogen, or two hydrogen. So they are different from each other only by one hydrogen, by one hydrogen atom. So they are conjugate acid-base pair. But which one is acid? Which one is the base? Oh, I remember teacher م.هۆگر told me that acid always has one hydrogen more than the base. So it's acid, it's base. It's base. It has a potential to receiving a proton. Okay? You see? It's very easy, conjugates. And now we have more idea about a conjugate acid-base pair. A conjugate acid and conjugate base from the pairs. Well, we have this reaction, NH3 plus H2O to producing NH4 and OH. How many conjugates do we get? Look, conjugates do you get? We have NH4 and NH3. They are differ from each other by one proton. So which one is the acid? Of course, NH4 has one hydrogen more. for OH and H2O. OH and H2O, they are a conjugate also. They only differ by one hydrogen atom. H2O is acid, OH is the base. So now I'll tell you something that they can be a conjugate, so please don't be confused when you see these pairs, NH3 and NH4. They are a conjugate, or NH3 and NH2 negative. They are a conjugate. They are different from each other by one hydrogen atom. Okay, H2O, H3O, a conjugate, it's a conjugate. H2O, OH, negative. Oh, they are a conjugate also, so don't confuse about here. The acid always has one proton more, the base has one proton less. In a conjugate acid-base pair, acid have always what? One proton more than the base. Let's continue. Now, in this reaction, when a question says in this reaction, we should follow the reaction only. We should follow the reaction, don't forget. Look, in this reaction, HF plus H2O to producing hydronium and fluoride. The conjugate acid-base pair is, look, H2O and HF, no, it's not conjugate. However, they are different from each other by one proton, but what about the negative side? It's fluorine, it's oxygen. We should have the same atom, the same thing for the negative side, and then for the positive side, we have the difference by one proton. Okay, it's not conjugate, simply. It's not conjugate. It is a conjugate acid-base pair, but we should check that we have that conjugate acid-base pair in the reaction or not. Because of it says in this reaction. So it should be a conjugate acid-base pair and should be present in the reaction at the same time. So it's conjugate acid-base pair. No, it's not conjugate. Well, what will happen if you have this answer instead of D? Well, suppose that D says we have H2SO4 and HSO4 negative 1. Oh, teacher, it's conjugate acid-base pair also. Yes, it's conjugate acid-base pair. But do we have that one in this reaction? No, we don't have, so it's not right. It should be a conjugate pair and it must present in the reaction at the same time. Because of this is a condition of this reaction, of this question, which is the reaction. Which of the following is a conjugate acid-base pair? Look, H and OH, no, they are different by one oxygen. It should be by one hydrogen. It's a conjugate acid-base pair, right? B. It's not. Simply. In this reaction, HPO4 negative 2H2O, the conjugate acid-base pair, look, it's pair. Yes, it's pair, teacher. And do we get this pair in this reaction? Yes, it's very important. Well, it's conjugate acid-base pair. But do we have this pair in this reaction? No, so it's not right. But they are different from each other by one hydrogen. Okay, it's conjugate acid-base pair, but without this reaction. Because of we don't have that one in this reaction. Okay, understand. HPO4 negative 2 and PO4 negative 3. Yeah, it's a conjugate acid-base pair, but let's follow. There's a priority, the reaction. Oh, we have that one in the reaction. So it's the right answer, okay. Because we have all of them answer and it's not right, so that means they are wrong. In the following, which of the following is a conjugate acid-base pair? Yeah, it's conjugate also, so all of them are conjugate acid-base pair. But what will happen if we put this reaction in here? what will happen, excuse me, what will happen if we put this reaction in here? So the only right answer will be that one, because so we get only that one. So as long as the acid is stronger, the base is weaker. As long as the base is stronger, the acid is weaker. It's about a conjugate. So the stronger acid has the stronger preference for releasing for donating a proton, as the stronger base has a stronger preference for accepting or gaining a proton. Which substance? So that means conjugates are differ from each other by exactly contrast property. Okay. A substance with less preference for donating a protons. Well, we have preference for donating a proton. Donating a proton is a property for the acids. And it's less, so it means weak acid. But strong preference, it means strong. So it's weak acid. Okay. Its conjugate will be weak, will be strong. Acid will be base. Now we should look for the property of strong base. Strong preference for donating a proton, no. Base can attract, can gain a proton strongly. Strong preference for accepting a proton, yes. That's the right answer, accepting a proton. Now, a base will be stronger if its preference, okay, a base will be stronger if its preference high to attract a proton. High to attract the proton, the right answer. Now, let's detect the direction in the proton transfer reactions. Actually, we have one rule. The direction always will be from the strong to weak. From the direction will be just like that. Look. Strong, weak. Okay, strong, weak, because of always strong can win when it fights with the weaker. According to this rule, it's jungle rule. It's jungle rule. Okay, determine which direction is forward or reverse is favored in the following reaction. The first one is that. Well, how to answer this type of question? First of all, identify strong and weak. It's strong. Okay, if it's strong acid, so water will have strong property, so it will be strong base. Water strength always depends on the strength of the first electrolyte. If it's strong, it's strong. If it's weak, it's weak. Because we have more proton, so it should gain more proton. So it will be strong base. If it's suppose that it's weak acid, so we have less amount of proton, so it should gain less proton. It will be weak base. So if it's strong, it's strong. If it's acid, it's base. To producing H3O. So because of its strong base, so it will be weak acid. It's strong acid, it will be weak base. Teacher. Now we detected the strength of these components of the reaction. So now here we have strong, strong, we have weak, weak. That weak acid cannot compete this strong acid to releasing a proton, and that weak base cannot compete H2O to accepting a proton. That's why the reaction is forward, direct, for the front, from the stronger to the weaker. And let's do the same thing for this reaction. NH3 is weak base. Do you remember it's weak? So water will be weak also, but it's acid. So now, if it's weak base, it's strong acid. So if it's weak acid, it's strong base. Now, okay, now we have NH4 and OH. They can compete successfully with that acid and bases. So here we have stronger, here we have weaker. This is the reaction direction, reverse direction. Very good. Dear students, please, to answering a question about here, we should remember the list of the acid and the bases. Without that list, we will be in a big problem. So please don't take that list, list of acid and base easily. Please be serious. Memorize them. It's very important because it's not the only chapter that we need them. We need them for chapter 4, for chapter 7. So look, if you forget them, you're gonna face a big problem in the final examination terms. So hopefully you memorize anything that I recommend to you. and هیوادارم باشی تێگەیشتە بوون سوودتان لێ بینی بێ بەڕاستی ئەو تێبینانەی کەوا باسمان کرد سەرجەمیان زۆر زۆر بە سوودن لە بۆ شیکارکردنی پرسیارەکان ئەگەر ئەتولۆ بەندێ باش تێبگەی لە بەندەکانیت کە دڵنیا بە تایبەت بەندی 4 و بەندی 7 زۆر زۆر باش دەبی لەبەرەوە پێم باشە تکایە هەمووتان بە وردی لیستی ترش و تفتەکان لەبەر بکەم بە بەهێزی و بەلاوازیانەوە کە یارمەتەی زۆر زۆرتاندا لە بۆ شیکارکردنی ئەو پرسیارانە تاوانەی داهاتوو کە لە بابەتی ئەمفۆتێریەوە دەست پێ دەکەین ئەمفۆتێری کەمپاوندز بە خواتان دەسپێرم هەر سەلامەت بمێنن خواتان لەگەڵ